All right, welcome back. So this little short lecture, we're going to be talking about how systems of equations can get really big really fast, okay? This is one of the central themes. I really cannot overestimate the importance of this concept that all of the systems that we're dealing with in this class are very small, low-dimensional systems so that we can illustrate the methods simply and so that we can code them up quickly in MATLAB. But really, the examples we're talking about generalize to very large systems of equations very rapidly. So one example is this weather model that we've seen before. So I have some probability that today it's cloudy, nice, or rainy. And there's some probability connecting, if it's cloudy today, what the weather will be like tomorrow, and so on and so forth. And we found that we can write this down as a simple 3x3 system of equations. X, let's say x tomorrow equals a times x today, where a is a 3x3 matrix and x is a state vector that tells me what is the probability that it's rainy, nice, or cloudy. Okay? Sounds simple. But this can be the basis for a much more sophisticated model of the climate over the entire globe. Okay? So let's say I look at the Earth, and every square kilometer is given, I have some initial data on every square kilometer covering the entire globe on whether it's rainy, nice, or cloudy. But maybe I have even more information. I have the pressure and the temperature and the wind velocity, okay? And maybe I have how much sun load is coming down and how much evaporation is coming off of the ocean. Maybe I have lots of information for every point on this grid that covers the globe. Now my state might contain millions or even billions of pieces of information. And this matrix A is an astronomically large matrix telling me about the connections between my weather now and my weather at some future time. Again, instead of x today and x tomorrow, this might be x at right now and x 10 minutes from now or 20 minutes from now. Okay? So this is just one example of how our simple toy system can scale up to a very large system very quickly. Okay, let's think about another system. So we've also looked at a bridge truss. Where we have a number of segments which provide constraints. We have some loading. Maybe there's trucks driving by and I want to know when is this bridge going to fail? Or maybe more topically, I have some side force here. A truck hits the bridge and I want to know how much of a force will collapse my bridge. We can write this down as a relatively small systems of equation, Ax equals B, where B is my external load. A is some system of constraints on these metal members, and X will be the forces experienced by each of these members. Okay, this is a pretty simple system of linear equations. But let's say that I'm looking at a real bridge. In a real bridge, I might have hundreds of segments or even thousands of segments. Or in the limit of a flat concrete bridge, I might have a continuum of segments. So if we go to the screen real quick, I just want to show you some examples of some of the types of bridge trusses that I'm thinking about. So here we see bridges with tens or hundreds of members. And so these equations scale up very, very quickly, right? The Ax equals B becomes larger and larger the more complex my real system is. Okay, so this is just a short video demonstrating how quickly systems of equations can become really big, really fast. Okay, thank you.